In this lecture, in this unit, we're going to address measures of central tendency and z-scores. And in this video, we're going to focus on a relatively simple type of examination of central tendency, and that's the IQV and Q-scores. But to first address central tendency, and we saw examples of this in earlier lecture materials, in that we are attempting to compute one number and only one number that summarizes everyone's score, so all the scores in a sample or in a population. And this provides an indication of the location of one person's score relative to the sample or the population of interest, depending upon the research question. So the measure of central tendency is just by definition here is a score that summarizes just that what we talked about, the location of a distribution of that score within a distribution of a variable. And this helps to eliminate the need to examine every single score. So the clear advantage here is that we can come up with one number without having to simultaneously examine every score. But at times that will also provide us with a bit of a disadvantage unless we can couple that one score with a measure of the variability, which is what we'll also address in this unit. And the three measures of central tendency that are commonly used that we'll discuss in this unit is the mode, the median, and the mean. Another term for the mean is the average. But before we get to these more traditional quantitative measures of central tendency, I want to first begin with something referred to as the index of qualitative variation. And this is a way to track the dispersion or the variability when we have nominal and ordinal variables. The calculation for the index will range between 0.00, indicating no variability, to 1.0, which is a number that would indicate the maximum possible variation among a set of scores. And so the IQV is just that. It's a ratio of the actual variation. Okay, when I say the actual variation, that's what we observe in our sample. So we collect a sample of data, and of course not every value is going to be the same, but what we're interested in is how much of those scores vary. And this ratio is just that variation to what the maximum possible variation that could exist in those data or in that distribution. And this is the standard equation that has been developed to use to calculate the IQV. And in this case, the K refers to the number of variable response categories. In the next example, we're going to examine a dichotomous variable and apply that to the calculation of the index of qualitative variation. The other major term that we need to calculate here is the percent, or the sum of the percent squared, and we'll step through that example here shortly. And this is just simply that, the sum of the squared percentages of cases within each of the variable response categories. So if we have a dichotomous variable, based upon the definition, the dichotomous variable will have two different categories, and therefore we will only have to sum and add up two values here. So to work through this example, this is an example taken from the textbook here, and what we see here is that we have a dichotomous variable in the study that sampled a group of individuals that were classified as a visible minority, and another group of individuals classified as a non-visible minority. And so what is not illustrated on this table is the actual raw numbers within each. So you can imagine here that we first have to calculate the raw numbers, the n. From that, we can calculate the percent respective to each of the two categories in our dichotomous variable. So in this table, we have the percent. So 16.25% among the entire sample were classified as a visible minority, while 83.75% were classified as a non-visible minority. We know that these calculations were accurate if we sum vertically, and it should equal 100. Now, if you take this approach with a variable that has more than two categories, the percent values that you compute when added up should be very close to 100. If you have values after the decimal point, we can attribute those to rounding errors that do compound. So as long as your calculation is very close to 100, then we can have confidence that your percent values were done correctly. We then move to the far right column here, where we just simply take our 16.25 and we square it. Likewise with the 83.75, we square it and we sum vertically, and we end up with a sum value for the percent squared of 7,278.12. Now, this value in and of itself has very little value, but based upon the equation that's been established, it's going to be critical to include in order to gain a sense of how much our nominal variable here, the categories, vary with respect to each other. So we just go through the table, we identify our components in our equation, and now we substitute. So K refers to the number of categories. So here we see 1, 2 categories. We take the value that we summed vertically, we input it into our equation, and we see K appearing once again. 100% squared is an intrinsic part of the equation, and we just include it. So this would be a good time to pause the video, go through this calculation, and then restart the video, where I will then go through the step-by-step solution to calculating the IQV. Okay, presumably you've attempted this and you're restarting the video. So after we write out our equation, and then we go to our table and we substitute the values. So we know that K refers to the number of categories. Here we have 2 for our dichotomous variable, so we put the 2 in, we fill in the 2 for the K, and we take our value from the summed right side column, and we work through our calculations. We do everything inside the parentheses first, and we end up with these values. As you can see here, 2 minus 1 is a 1, and we complete our final step, and we have an IQV of 0.54. So when performing this calculation, the first thing to identify is whether your final answer is between 0 and 1.0. If your final answer is greater than 1, or is perhaps a negative value, then there was a calculation error. But barring that, a value of 0.54 is a ratio. So basically tells us that this amounts to a 54% variation between the two categories in our dichotomous variable. The meaningfulness of that really now depends upon the field of study and the research question. Moving on to another way to track the variation of different variables is what's called the interquartile range, or the calculation of Q. And Q functions by dividing up the data in a sample into quarters. And so it's by dividing data up into quarters, then that allows us to estimate what's called the first quartile, and the third quartile within that distribution. And so we can consider the quartile as a type of percentile. And this is a bit more of a crude measurement of percentile, but does provide us with a relatively easier calculation from an interpretation perspective, but we do lose some sensitivity in terms of getting to smaller percentiles. And so once again, as discussed in the previous lecture, the percentile refers to the point below which a specific percentage of cases will fall. So if we're talking about the 25th percentile, as we see here, the 25th percentile corresponds to what we call the first quartile. And so when referring to the first quartile, we're referring to that point below which 25% of the cases will fall. If we jump up to the third quartile, remember we've broken up our data into quarters here, the third quartile will refer to that point below which 75% of the cases will fall. And this illustration here on slide 6, what we see is that we have the low score on the left-hand side, so the single lowest score in our sample. We have the single highest score in our sample on the right-hand side, which establishes the range. And we see the data are broken up into quarters here, where we have Q1 referring to the low end. So at a value of Q1, we see that 25% of the scores lie below that. At Q3, we see Q3 as that percentile where 75% of the scores fall below, and Q is basically the middle 50%, which captures half of the data in our sample. And it's just simply a calculation of Q3 minus Q1 of the actual raw data. So Q3 refers to the raw data point. It's not 75, but it's the data point at Q3 subtract data point at Q1. That will give us the Q value. And so based upon those data, we can illustrate this with what's called a box plot. Technically, this is based on a 5-number summary. What we see here in this box plot, here we see our quartile, our Q range, and we also have the error bars. So the error bars here represent the low score, and in this case, if we're representing a monthly salary within the workplace, we see the lowest salary just above $1,500, the highest salary just below $6,000 for the month, and the middle line here being the M middle, that is the median within our distribution. So the low end of the box is the first quartile, the top end of the box or the higher end of the box is the third quartile, while the middle part of the box is the middle point or the median value in our sample. So this ends this first video of Unit 2.